Now, it's obviously a great deal of joy to read these Nobel lectures, and it's so inspiring, to see that how one approaches a complex task. Now, the other very important lesson from Bosch's lecture, which again I want you to pay heed to, okay, is that once you have developed a device, okay, then and some kind of core competency, then try and apply it, to maximum extent possible. Okay? Because that is the smartest thing to do. Okay, because you have to invest in a minimum amount of effort, to be able to do that, and so widen, the application of whatever you have developed. Like one of the students here, who's now doing his PhD in ICT. I mean, he developed an equipment, which is for uh, uh, basically an extractor, a rapid extractor, solid state. If you have solids, it extracts out constituents from that solid. Okay, and it's a very interesting unit that he has devised. Now he was initially focused specifically in trying to take out, let's say, carotene, or some lycopene, a particular red color that you get from tomato, and that's what he was working on. But today, he can actually utilize his equipment to do a lot more. I mean, there are so many different things that you can look at. You can look at interesting things like extracting tea from tea leaves under cold conditions. I mean, you can do all kinds of interesting work, okay, with that. So, what gives him that ability? He has the equipment. So he can expand the utility of that equipment. Okay, so that is something that you must do, and look at how BASF did that. Okay, what and he says that the development of the ammonia manufacturing process, which partly as a result of Germany's isolation owing to the war, was perfected in a relatively short space of time by harnessing all our efforts and resources, has also, of course, stimulated the development of other reactions which proceed markedly better under high pressure than under atmospheric pressure. Because, and that was great that they could look at that. And one of the first that they looked at was methanol synthesis. They realized that, look, what am I starting with? I mean, if I'm when I'm doing steam reforming, I'm getting syngas, and then of course they were doing air reforming and basically getting hydrogen and nitrogen. But if I take that intermediate, which is syngas, okay, and then I can react it and form methanol. So they conceived the idea, of methanol formation. They also had figured out, I think, at that time, that it's an exothermic process, and then they went about, discovering catalysts which might enable one to make methanol. I mean, that again would have been an unbelievable effort, to develop a new catalyst for production of methanol. But they succeeded, and I'm sure, their ability that they made a reactor which they could operate round the clock. Obviously that would have made their job a bit easier. That you can do so many reactions, and then the chances that you'll come up with a catalyst are higher. Okay, and so then they invented the zinc oxide, chromium oxide catalyst, and came up with again one of the blockbuster products that produced. Now there was another, and very very interesting thing that Bosch says, especially today, it's extremely relevant. Okay, like for example, this whole business of pollution. Okay, And pollutants are what? They're present in ppm levels, right? And the norms, pollution norms are becoming even stricter. Okay, and they can people are saying even ppb in some cases. Okay, like dioxin, which gets released into the atmosphere. It can cause cancer. The levels are very stringent. Okay, now what happens is that if I have to remove, let's say, traces of impurities, okay, now what really would be the best way of trying to take out traces of impurities from something? Let's say if I've got a some gas or atmosphere, and I'm trying to remove traces of impurities.
Scrubber we can.
Scrubber, right? Yeah.
Yes.
Okay.
We can absorb it on something. We can
Right.
absorb
So
it.
I would say, you have adsorbent scrubbers, right? If the concentration of the impurities is higher, will the scrubbing be better, or if the concentration is lower?
It will be better at higher concentration.
It will be better at higher concentration. Okay. So let's put it down. Okay. I am so glad that you've mentioned, but let me put. Uh, Say if one has to remove impurities from gaseous emissions, okay, emissions, or even from the atmosphere. It may be that in the future, you see, I mean, because of this greenhouse warming and carbon dioxide, maybe there will be a huge amount of work in trying to extract carbon dioxide from the atmosphere, to reduce, lower the temperature of our atmosphere. And carbon dioxide could be a feedstock which will be used. So that could happen. That could be a very important problem to work on. Some of you, or maybe 10 of you, can do your PhD in something like that. Is that important? Okay. So now, and then you said, student, removed by scrubbing or adsorption, and both would be better at higher concentrations. Impurities. What you tried to say, have I got it right?
Yes, sir.
Is correct what I've written?
Yes.
Okay. All right. So, that's wonderful. Okay. Now, so how can you reach higher concentrations or higher partial pressures? If I've got a low concentration, how can I increase the partial pressure?
By pressurization.
Absolutely. Absolutely. Wonderful. And how? Pressurization. No? So you can see that things are to be logically concluded. You ask questions, then see what is an answer. How do I achieve and how do I solve the problem to have that answer? And so what BASF said is that, look, we understand high pressure, and so this would be a wonderful way of trying to remove impurities. So, for example, carbon monoxide is one of the impurities that they were particular about. I'm not even talking about impurities in general. You would have seen that they had sensors for monitoring carbon monoxide, so they wanted to get rid of it. Okay, and he says it over here, so beautifully. Uh, Let us assume that 0.01% CO has to be removed from a gas mixture. Technically, at the high speed of the gas flow and low pressure, this is practically impossible by scrubbing with an adsorbent, but very easy at 200 atmosphere with a carbon monoxide partial pressure of 1 by 50 atmosphere. No? So what looks like an extremely difficult problem becomes a lot easier to solve. So, for example, if you have to look at flue gas, and all the emissions which you need to deal with in flue gas, okay, and maybe the way to go would be really do a downstream pressurizing of flue gas, and then actually make the process of removing impurities easier. Of course, in anything there will be an energy penalty. Okay, that's always there, but you can reduce, the penalty like we found in the liquefaction of ammonia. That they could integrate with the process which is already operating at high pressure. So obviously, you will look at smart things like that where there is already a pressure that is created. Then exploit the pressure. Rather than letting it go up into the atmosphere as 1 atmosphere pressure. All clear? Everybody understood? All clear?
Yes, sir.
Yes, sir.
Okay. Okay. So let us look now at some of the very important lessons which one can learn. Actually both from the work of Haber and Bosch, particularly from the work of Bosch. So I just tried to list out, some of the lessons that came in my mind. Okay, now you can actually add to the list, or if you think that some of the things that have been written here are not that important, okay, or irrelevant, you can remove it. I mean, that's entirely your prerogative, and I hope that you will add to the list. Okay, a clear and important goal. In this case, it was the fixing of atmospheric nitrogen more energy efficiently than achieved through the Birkelandite and cyanamide processes, and the passion to succeed per innovation. So that's very important. It's not just having a goal, but how passionate are you really to succeed in that goal. And so that's the first thing that came to me, and it came through loud and clear, from the work of Haber. He was passionate about solving the problem, okay? And he had that clear understanding of the limitations of the Birkelandite and cyanamide processes. Haber's success rested on basic understanding of thermodynamics, development of high pressure reactor, and fortuitous discovery of osmium and uranium as low temperature catalysts. Now, the reason why I say fortuitous is it is not as if, of course, Haber might object from his grave, to my saying fortuitous. So, what do you mean? I looked at the periodic table, and I identified osmium as falling in the same group, but the point is, I'm very sure that they would have experimented with numerous catalysts, and he must have been lucky to have got osmium. I don't believe that that's the only catalyst that he experimented with, and same is the case with uranium. Okay? But doesn't matter what, whether it was fortuitous or whether it was planned, that he was very successful, and the guiding principle was thermodynamics. Guiding principle was thermodynamics. Facilitator was high pressure reactor. Okay, and discovery process was the identification of catalysts that could do the job at lower temperatures and therefore helped in the overall conversion. Third, company vision, holistic understanding of issues, correct diagnosis, like being able to diagnose the why the converter gave way. What happened? Okay. Eye on practical solutions. Put a liner. Don't wait to understand everything about the iron catalyst. Just get going. Okay. And close coordination and teamwork was a powerful combination in the case of BASF. What were they doing? Somebody was continuously doing reactions with the catalyst, and then just giving information on what is the performance, and another team was trying to improve that catalyst. Okay? And likewise, whether it was the steam reforming and air reforming processes or this or that, you can imagine, all right, the complex teamwork which had to be managed, okay, within BASF. Having a unique skill or equipment always gives an edge. For Haber, it was the high pressure reactor. So he could do things which Nernst and Le Chatelier could not do, or Oswald for that matter. None of them could do it. And Nernst, not Nernst, Bosch, because they could not only make it in the laboratory, they had large scale high pressure plants which they had developed. So it gave them an edge in subsequently inventing the processes for methanol, inventing the process for urea, all an outcome of the fact that they had a big high pressure reactor which was perfectly in order, working safely. Networking and cross process learning are of great value. I'm sure that Haber networked with Linde, and would have learned a lot from the liquefaction of air, and been able to really come up with the with his own reactor, and so that would have been of phenomenal value, I think, to Haber, and also likewise the interaction that he had with Nernst, and Nernst telling him to look at the thermodynamics of the process. What next? This is extremely important. Okay, always, if you're an innovator, one is that you can bask in the past glory, and you can say, I achieved this and fantastic, and for the rest of your life, you can bask in that glory. You can do that, no problem. But there are some who are absolutely, restless, and they say, what next? What next? What can I do after this? And so that's how they were able to, the technology platform that they created, they were able to launch in so many directions, whether it is methanol or urea, or being to carry out high pressure removal of impurities. All of it was came out of this urge, of what next. The importance of trial and error in catalyst discovery. Okay? Don't let anyone fool you. 20,000 experiments mentioned by Bosch. Okay? 20,000 experiments. So even after having found this Swedish ore, and drawing inspiration from what? The work of Ramsay and Young, said that let's go back to scratch. Maybe Ramsay and Young in turn drew inspiration from nature and from the iron sulfur protein, the enzyme that actually fixes nitrogen in nature. Maybe that's how they had the idea of iron and molybdenum. I don't know. I will be completely wrong. Okay, but it seems to me that that could have been a source of inspiration. You know. Both Nobel laureates presented their work with great clarity and lucidity. Okay? This is another, I mean, especially Haber, his way of writing is so beautiful. The way he writes, that why can they do it? Because they are the inventors. They know what was important to them. Okay? So obviously they can, the clarity and lucidity with which they can write, others can't. I mean, because I will be writing a third person account, whereas you are hearing it from the horse's mouth. That person can tell you exactly, what propelled them, okay? Provided they're speaking the truth, okay? And they're not trying to hide something. That's also important. Now, and the last word has not been spoken. In fact, Haber himself says that who knows, in future we might go the plant way, green plants, leguminous plants, and maybe there will be brilliant discoveries, and we will be doing it by nitrogen fixation as nature does it, and there will be unbelievably efficient enzymes, which can do the job. You know. So the last word has not been spoken. Okay? And so again, I think it's very important that I mention this. Now, a couple of things. We have got so brain. If I ask you, hey, tell me what is the Haber-Bosch process? First thing that people will, I'm sure, say, tell me what is the Haber-Bosch process? What's the, if I have to write the overall stoichiometry, what is it? What am I starting with and what am I finishing with? If someone I ask you to write down the reaction, write the reaction of the Haber-Bosch process, the starting materials and the final products. That's how we write reactions, right?
Yes, sir. So nitrogen plus hydrogen.
Nitrogen plus hydrogen, right?
So N2 plus 3H2 giving 2NH3.
Correct. That's what you'll write, isn't it? Huh?
Yes, sir.
Anyone who differs or anything else? Well, what did you really start with? No, I did not start with nitrogen and hydrogen. I started with natural gas. I did steam reforming with water, with steam. Okay? And then I introduced air. Okay? And carried out, that's how I got rid of all the oxygen. Okay. And and finally I ended up with nitrogen and hydrogen. Okay. So effectively, what did I have? Maybe I should have written this as methane plus nitrogen plus oxygen plus water, giving me, okay, nitrogen plus hydrogen plus CO2 plus water. The water was removed by taking it below the dew point. The carbon dioxide was removed by absorbing in amine solvent. Okay, and I was left with nitrogen and hydrogen. Which then is what gave me ammonia. So ultimately, what did I get? I got carbon dioxide as my byproduct, and I got ammonia as my principal product. Okay, and then these two were combined to make urea. So really, if I have to write, what is the stoichiometry of this reaction? It is effectively methane, which is my feedstock, right? Right or wrong?
Yes, right.
Yes.
And not surprisingly, you see, this is a, it's known as a Verul's curve, okay? And, it actually shows what is the trend of ammonia production versus what is the trend of natural gas production. Because why? Because ammonia is really coming from natural gas. So if there is some shock felt in natural gas, that shock will also be felt in ammonia. And it's amazing. I mean, that literally it's absolutely mimicking this graph. This is the graph for natural gas. And what does this plot tell you? That we are absolutely at the peak of natural gas production, and from here it's all going to be downhill. Okay, by 2030 you will be somewhere here. Okay, natural gas production will come down. It's going to come down further. Okay, and people are predicting that maybe about 40 to 50 years is that all we have got left as far as crude oil and natural gas are concerned. It's not a limitless supply. Okay, so the question then is that if this Verul's curve is going to follow, and then if I have to write all black, black, black over here, what does it mean that my urea production will come down? Obviously, that's not going to be acceptable because billions of people will die. The world's population is set to increase by another 2 billion by 2050. That's the projection. Where are you going to feed all these people? Okay, if that were to happen. In fact, we want a break from this, and we want it to go up and up, not like this. Okay, and so that's the issue. And that's also the critical importance of actually understanding really what is the stoichiometry. So if ever anyone asks you, you should say, although people write it at that, nitrogen plus hydrogen, frankly, we ought to be writing it like this. Now, so, there has to be a complete break, right, from everything that you have learned. Not a complete break, but a sufficiently radical break. One thing is for sure, as we discussed, that natural gas and crude oil are going to come down. There's no question about that. Okay? Now, natural gas and crude oil are mostly used actually to burn. Okay? A lot of it is used, natural gas is used for all the power, all of Europe has switched over from coal to natural gas, so that's going to hasten the decline of natural gas. Now, one very, very smart thing to do would be that you say, stop, let us not be stupid and use natural gas for just burning and getting power. Let us conserve the natural gas for making urea. And let us try to find another solution to energy, because I will require this natural gas. But, it doesn't seem that people will have that vision. Okay, that's what I would do. I would have stopped it. I would have said, no more natural gas for your power. Please conserve it, for chemical feedstock. And you go and solve the other problem, of how to clean up coal and generate power. Okay? Now, the other alternative, which people are hoping for, and I don't know whether it will finally happen, but every day there is so much of advance being made that it looks like, in 20, 30 years, that nuclear fusion will become a reality. Now, if nuclear fusion becomes a reality, then you are going to be talking about limitless power. So what today we consider as, so intertwined with fossil fuel, burning for generating power, that it likely will come from the nuclear sources, whether it is nuclear fission or the most ideal would be nuclear fusion. Of course, solar energy and wind energy would make massive contributions. I'm sure about that. But to me, it seems very, very unlikely, okay, that those will be able to substitute for the demand of fossil fuel. To me, it seems that one of these nuclear processes better click, and especially nuclear fusion. Otherwise, we will be in big trouble. Now, if that happens, and all of this is if, okay, but that's how you build scenarios. If that happens, if I have got abundant energy, electrical power, then you know why I will do liquefaction of air and I'll get my nitrogen. I will do electrolysis of water, you know, because there's abundant power and I'll generate hydrogen. What's the problem? Okay. So 30 years from now, don't be surprised if you are able to write, you know, the actual stoichiometry, which is nitrogen plus hydrogen giving you ammonia, and those really coming from the use of electrical power, you know, green power, which doesn't generate carbon dioxide. Okay, so that would be great. And for that matter, you see, if I am able to do this, I mean, I might as well also look at the Birkelandite process then. Well, and let's make nitric acid. May not be all of it as nitric acid. Maybe I'll make 50% nitric acid. I'll make 50% ammonia, and I'll make ammonium nitrate. Okay, so the scenario could be very, very different. Okay, 20, 30 years from now. Okay, and you know, I mean, although we've been talking about these since 2015, I see actual people, they've started writing, publishing papers. So you can have a look. You know, I'll see if I can get this paper and send to you. Okay, and also it will be interesting to look at, you know, what could be other worthy innovations in the Haber-Bosch process. Okay? I mean, I'm not telling you, you know, some ideas that came to my mind. There will always be a motivation to make a better catalyst. So the last word has not been spoken as far as the catalyst is concerned. You know, I'm sure there will be improvements. Maybe even to make it more moisture tolerant or make it more CO tolerant or whatever. I would have thought that it will be very interesting to be able to carry out very controlled combustion in my reactor, and I could generate the pressure that I require from that. So I don't need compressors there. I will actually use, you know, the reaction itself, you know, to as a means of generating pressure. For example, if I start with air and hydrogen, I'll consume up all of the oxygen and I'll be left with nitrogen and hydrogen. You know, if I'm injecting hydrogen, okay, and if I can do it in a controlled manner, maybe I can get rid of a compressor, if that's possible. Okay. So those would be the kinds of things that I look at. Tell me one thing. Do you see some other potentially big application of ammonia in future? Can you envisage? Can you think of any other use? Anyone? No? Just take a wild guess. What do we need in large amounts?
We need energy.
We need energy. Very good. You need energy. Okay? And you know, you also need energy. For example, what kind of state of matter is diesel and petrol and all?
Liquid.
Liquid. Okay. So you know, because it's so easy to transport, na? You could have a very interesting situation where ammonia is actually used as a fuel, just in place of things like petrol and all. I mean, it's hard to imagine because we are so brainwashed into, you know, writing the equation for a hydrocarbon and reacting with oxygen and going to carbon dioxide and water and generating a lot of energy. But believe me, and especially the Japanese are doing a huge amount of work today, okay, on the possible use of ammonia as a liquid fuel. And you see, don't forget, it's so easy to liquefy ammonia once you integrate it with the process. Okay, and so once I've done that, I can put ammonia into tanks, fuel tanks. Okay, and it'll just go and run on that, rather than on petrol. Okay? And look, when would I do that? If, for example, if those other scenarios, what I told you about of having abundant electrical energy, if those scenarios work, then it's possible that I can make plenty of ammonia. There's no problem. I'll make as much ammonia as you want. Okay, and
So,
if we, yeah,
so, but like there can be one problem with that is that it has a very foul smell.
absolutely.
Also, sir, ammonia can be absorbed by our skin, so that can be toxic also.
Yes, wonderful. But problems, right? That's what you're saying, isn't it? Huh?
Yes.
Yes.
Absolutely. And so this is the interesting things that what happens is that yes, there will be huge problems, and it's possible that you will not be able to get 100% conversion, and it might be a very toxic environment that will create. Obviously, the people who are working on this are well aware of that. And so if they are going to try and solve the problem, they will solve it with that level of perfection. You understand what I'm trying to say?
Yes.
Okay, so naturally, no one is going to allow you to spew out ammonia. There will be very strict emission norms in the discharge of ammonia, and that's also the reason why people are, spending a huge amount of effort in improving the design of these burners, which you can use to combust ammonia. But why is there so much of interest in ammonia? The reason is because if I write the stoichiometry of the reaction, what are we writing? It's 4 ammonia plus 3 O2 forming nitrogen plus water. No greenhouse gas. Okay? And second, don't forget that if I have to run transport, mobility, if I have to have, and if you say the only thing everybody is talking about electric cars, but electric cars will require batteries. It's not for free unless you can, maybe in the future what you will have, just like we have train lines and tram lines which are connected to a electric line, right, on the top, and you run these locomotives. In Calcutta the trams run like that. Okay, so maybe in future what you'll have is you'll have tracks, which are electrically charged, and nobody will fill up anything. You'll just run your vehicle using that, and you'll be charged by the power consumption. It's like an electricity meter. Okay? But those are very, very futuristic. And let's assume that the option will be either a liquid fuel, okay, or it will be a battery. If it's electric vehicle, I might say, and there are already, as much as a battery, people are looking at hydrogen as a fuel. Okay, but if I'm going to look at hydrogen, I also might as well look at ammonia, because ammonia is certainly much easier to liquefy and store compared to hydrogen. But ammonia has the problems that you all have mentioned. So obviously those have got to be solved. Okay? So I hope you can see, and what is the primary motivation? primary motivation is got a very high delta H. So I can get a lot of energy from this combustion. And it only produces nitrogen provided there is no leakage of ammonia into the atmosphere. So there's a huge amount of work going on things like what is known as the swirl combustor. You can go and find out what is a swirl combustor, how to make a more efficient design of a swirl combustor. All your knowledge of engineering maybe you can use. And we also know what are the flammability limits of ammonia. If I have got completely dry air, or if I have got a very humid air atmosphere, then those limits have been worked out. For dry air and humid air. Okay, so all of these things, okay, are very very important. And believe me, some really big brains in the world, okay, and people who are extremely visionary, okay, are actually working on the possible future use of ammonia as a fuel. Any questions?
So, but
Yes.
one thing is that when you compare any petroleum fuel and ammonia, doesn't ammonia give a very less calorific value?
Oh yeah, compared to your hydrocarbon, it does. What I will do is, like you can actually convert this like natural gas, for example, is it gives you about something like 10,000 kilocalorie per kilogram of natural gas. Okay, so if you take methane, all right, and ammonia, their molecular weights are similar, right? 16 and 17. Okay.
Yes.
So just see how much it comes to. We can just work it out right now. 316.8. Okay. Let's say if I've got 316.8 kilojoule per mole. So I
Yes, sir,
put
I've done it. It's around 20 megajoules.
20 megajoules, right?
Yes, sir. Per kg.
Per kg.
Yes, sir.
Right? So 20 megajoules is 20,000 kilo, which comes to about 5,000 kilocalorie per kilogram, right?
Yes, sir.
Approximately,
Yes,
huh?
sir.
Correct or
Yes, yes.
not?
Yes, yes.
So we are talking about within a factor of 2, and that is for natural gas. For if I take diesel and all, it will be closer to about 9,000. You understand? 8 to 9,000.
Yes.
And coal is 5,000, 4,000. Not so bad, no?
Okay, okay.
And by the way, I hope you can also understand that, even if you have these questions, how easy it is to quickly come up with a solution. Like you can quickly do a calculation and see, right? It doesn't
Yes,
have
sir.
to be left as a guessing game. All right. So I hope you have understood the total thing about nitrogen fixation and what the future holds for us, and all the excitement that you might see in the future.